हेलो एवरीवन, वेलकम टू क्लास 12 फॉर CFA लेवल 1 क्वांट्स। आज के क्लास में हम एक नया टॉपिक स्टार्ट करेंगे। टॉपिक के साथ साथ आज हम एक नया कंसेप्ट भी स्टार्ट करेंगे। तो प्रीवियस दो क्लासेस में हम लोगों ने स्टैटिस्टिकल मेजर्स ऑफ सेंट्रल टेंडेंसी किया। आज के क्लास में हम क्वांटाइल्स ऑफ एंड मेजर ऑफ डिस्पर्शन स्टार्ट करेंगे। तो आज का क्लास में हम ये पूरा क्वांटाइल्स करने वाले हैं, ठीक है, विथ ऑल द एग्जाम्पल्स, विथ ऑल द रियल लाइफ सिचुएशंस। फिर हम मेजर्स ऑफ डिस्पर्शन स्टार्ट करेंगे। हम समझेंगे डिस्पर्शन क्या होता है, उसके अंदर हम रेंज करेंगे, मीन एब्सोल्यूट डेविएशन करेंगे, वेरिएंस स्टैंडर्ड डेविएशन करेंगे। और मैं बता देता हूं, ये जो टॉपिक है वेरिएंस एंड स्टैंडर्ड डेविएशन, ये मोस्ट इंपॉर्टेंट टॉपिक है पूरा क्वांट्स का। मैं बता दे रहा हूँ क्यों। क्योंकि ये वेरिएंस एंड स्टैंडर्ड डेविएशन आपको डेरिवेटिव में भी काम आता है, आपको कॉर्पोरेट इशूअर में भी काम आता है, पोर्टफोलियो मैनेजमेंट में भी काम आता है, हर जगह काम आता है। तो ये कॉन्सेप्ट अपना बिल्डिंग ब्लॉक है। जहां जहां रिस्क एडजस्टेड रिटर्न्स की बातें होती है, वहां पे वेरिएंस और स्टैंडर्ड डेविएशन आता ही है, ठीक है। तो ये बहुत इंपॉर्टेंट है, इसलिए हमने इस पे बहुत एग्जॉस्टिवली टाइम दिया है विद अ लॉट ऑफ एग्जांपल्स, लॉट ऑफ ग्राफ्स, लॉट ऑफ ड्राइंग्स। तो मैं होप करूंगा आप अच्छे से देखो। हमने यहाँ तक किया है कॉन्सेप्ट ऑफ सैंपल्स तक। तो ये एक पन्ना हम लोगों ने पूरा किया है ये वाले क्लास में, एंड ये वाला पोर्शन पूरा किया क्वांटाइल्स एंड मेजर ऑफ डिस्पर्शन इनिशियल, ठीक है। आई होप आपको क्लास पसंद आए एंड मिलेंगे अगला क्लास में।
Kurtosis. So today we will start firstly with quantiles. Now what does quantile states? So I just want you to imagine the entire one data set, right? So I want you to imagine a data set. So before we get into the definition of quantiles, let us consider my data set is like this. So this is my data set. So I'm assuming this is my data set. Right. Now suppose if I ask you that please divide the entire data set such that I receive 10 equal parts of the data set. Let me just repeat what I tried to say. I said that please divide the data such that I receive 10 equal parts of the data set. So if this is the entire data, what I will do? I'll do 1, I'll do 2, then I'll do 3, 4, then I'll do 5, 6, 7, 8, and 9. Assuming all of areas of all of them are equal. So what I've done, I have divided the data set into 10 equal parts. However, at the same time, I could have asked you to divide the data set into 4 equal parts. Then what would have been my approach? My approach would have been to divide the data set into 4 equal parts. So firstly, I would have done this, then I would have done this, then I would have done this, and the remaining part. So here I'll get 1, again I'll get 2, again I'll get 3, and again I'll get 4. Again, if I ask you to divide the data into 2 equal halves, now I want you to understand and mark what I'm trying to say. I'm asking you to divide the entire data set into 2 equal halves. So what will I do? I'll divide the data from over here. I'll get 1 and I'll get 2. 2 equal halves, right? So if you could recall what we had done in the last class, median was a measure that divided the data into 2 equal halves. So what we are doing over here with the green color pen is actually simply this value that we are computing, right? Which divides the data into 2 equal halves is actually median, right? However, similarly, at the same time, we do have names for those numbers which actually divide, those data points which actually divide the data into either 4 equal halves, or it divides the data into 10 equal halves, or it divides the data into 100 equal halves. Right. However, the measure which divides the data into 2 equal halves is median. We have already done it. We have looked into the details with respect to the calculation, with respect to the formula, and we are sorted with it, right? However, if I ask you to divide the data in 4 equal halves, again I can ask you to divide the data into 10 equal halves, or I can ask you to divide the data into 100 equal halves, right? So what does that mean? It means that we can divide our data sets into n number of equal halves, right? It can be, if we are dividing it in 2 equal halves, it becomes median. If I am dividing it in four equal halves, then it will be quartiles. So this is known as quartiles. So I'm throwing a new term in front of you. It will be quartiles. So I'm throwing a new term in front of you, right? Similarly, if I'm breaking the data into 100 equal halves, and why I'm taking this, I'm not taking 10 equal halves, because when I break the data into 100 equal halves, the term that I will use is actually familiar with you. It will be percentile. And I'm quite sure that since you are studying this curriculum, you are into this curriculum, you would be understanding that even CFA Institute gives each and every student, marks each and every student based on the percentile itself, right? You will pass or fail will be dependent upon the percentile, which means that CFA Institute itself divides the entire data set. Now for CFA Institute, the entire data set would be all the candidates appearing in the exam, right? For CFA Institute, the population set or the data set would be all the candidates appearing in the exam, right? It would divide that data into 100 equal halves and then determine which student is falling in which half. 100 equal portions, right? So what will CFA Institute do? If this is the total number of students appearing in the exam, then CFA Institute will divide it in 100 equal parts and try to identify how many number of students are falling in which part. And then CFA Institute will decide, will set a minimum threshold that if students are below this, if students are below a given threshold, for example, 70th part, right? So if CFA Institute decides that a student who is, as per his score, as per the score he has achieved, if he is below the 70th portion of the entire data, so if the data would be created by the number of candidates appearing in the exam and the score they have achieved while they have given the exam, now CFA Institute can identify that I want to mark the student as present if his score is lying above 70th part of the data, right? Now what will CFA Institute do? Out of the total number of candidates appearing and giving the exam and achieving a score, CFA Institute will divide that entire data into 100 equal halves, 100 equal parts. Now the next step would be to determine a minimum threshold. So I'm just giving an example with respect to CFA so that you can connect it better, the example, then only you will be able to understand what I am trying to say. So firstly, it will have a data of all the students appearing, and secondly, it will have a data with respect to the scores of each and every student, right? Third, it will have to decide a minimum threshold as to I will declare a student as pass only when his score is actually falling above. His score is actually, if my threshold is this, if the CFA Institute has kept a threshold of this, then CFA Institute might decide that a student will pass if his score is above this threshold, right? His score is above this threshold. Now this threshold which institute has decided is not on the basis of score, which means that if the exam is of 100 marks, I'm just taking an example, right? Exam is not of 100 marks. So I'm just taking an example on the scale of 100. If exam is of 100 marks, usually what happens, institute will decide that for all students appearing achieving more than 70%, Mark my words, I am here telling 70%, which means that score of 70. Any student having a score of 70 will clear the exam, right? However, CFA Institute is not doing like that. The CFA Institute, the entire data that CFA Institute has of the number of students appearing and the scores of each student, CFA Institute will divide them into 100 equal portions, right? And then bunch each and every student into each and every portions, right? And then decide as to students who are above the 70th portion. So if you visualize the data, if this is the total number of students appearing in the exam, if this is the total number of students appearing in the exam, and what I have done, I have actually students. So if I draw students, so institute will block them. Institute will actually classify them into different blocks based on the marks they have achieved, right? And suppose institute has decided that my minimum threshold would be this, which means that all the students which are who actually appeared in this block, all the students who appeared in this block basis their marks, right? All the students who appeared in this block basis their marks will clear the exam, and all the students who were in this block, so all the students who were in this block would not clear the exam, right? So what I am doing, I am actually breaking my entire data set. So this was my entire data set, the one I am marking now. This was my entire data set. I have broken this data set into 100 equal portions, and then I'm identifying, right? Then I'm identifying the data in each of the portion, right? So this activity, this breaking of the data into equal parts, it can be either 2 equal parts, it can be either 4 equal parts, it can be either 5 equal parts, 10 equal parts, 50 equal parts, 100 equal parts, and each of the equal part has some name. For example, 2 equal halves is named as median, 4 equal halves are known as quartiles, 100 equal halves are known as percentile. Similarly, we have quintiles, right? So these have a separate name. However, a common name assigned to all this. So if I have different names such as median, I have something known as percentile, I have something known as quartile, I have something known as quintiles. So a common name assigned to all of them is quantiles. So this actually you can draw a similarity with respect to squares and rectangles in maths, right? So we all have studied geometry in our childhood days. So if you look at figure, right? If you look at the geometrical figures, so this was known as triangle. This was known as square, assuming all the sides are equal. This was known as rectangle, right? However, both of them again, this or this or this, all of them means all the four shaped figure, four sided figure, all four sided figure were known as quadrilateral, right? So even square was a quadrilateral, although it had a specific name where all the four sides were equal. Rectangle was also a quadrilateral where the opposite sides were equal to each other, right? Similarly, in the given example that we were discussing, we do have median, which break the data into two equal halves. We do have quartiles, which break the data into four equal halves. We do have percentile, breaking the data into 100 equal portions. We do have quintiles, but they all have a common name. They all have a general name, and that generic name is known as quantiles, right? So with this, we will now move to the definition of what quantile says. However, we have already seen the concept of quantile. Quantile has nothing more to explain in it. So quantile states that it is a general term. So as we have already discussed, it is a generic term. So we have already discussed quantiles is a generic term, right? So we have marked generic over here. For a value. So quantile is a generic term for a value. Similarly, median was a specific term for a value which broke the data set into two equal halves, right? So it is a value. Now what value it is? At or below which a stated proportion of data is in a distribution lies. Now reading this definition, it could be very confusing, right? Because in order to avoid those confusion, I gave those examples in the first place so as to make you understand that quantile is nothing. It is nothing extra that you are studying. It is simply a measure which breaks the data into equal halves. It can be 10, 100, 5, 20, 50, 75. It is 2. So quantile is nothing. It breaks the population into parts, right? So if you take examples, now quartile is also an example of quantile. Decile, which breaks the data into 10 parts. Quintiles, as I was mentioning, it breaks the data into 5 parts. Percentile, breaking the data into 100 parts, right? So they all are quantile. So quantile is generic name, right? Now what does it state? Where an observation has n data points. So we have already discussed when we were doing mean that n data point means that, for example, if an observation has 10 data, so in that situation n would be equal to 10. So n data point means the number of observation within the data we are given with, right? And we need to determine. So we'll start with the beginning. It states that where an observation has n data point, which means that the number of observations we have, right? Where an observation has n data point, and we need to determine the value of observation at yth percentile. Then that value would be n plus 1 into y by 100. Right? The value would be n plus 1 into y by 100. Now what does it mean? So we'll try to understand it from an example per se. So it is nothing new that it is saying. It is simply that the language is a bit complicated, which is given. So if we take a data point, suppose if we take data of again 10 students. Now suppose if we increase the data, right? So that as to create diversity in the example, 15 students. Marks, again the score they have achieved 42, 51, and here I am directly arranging the data into in an ascending order, right? So that our time is the time invested is less, because again when we are talking about quantiles, similarly the discussion we had with median, that the arrangement of the data is important, right? Similarly in quantiles, quantiles as in the generic term, so whether it be a percentile, whether it be a quartile, whether it be a decile, or whether it be a quintile, the arrangement of the data is important, right? So one important thing that I want you to write over here and mark it is that arrangement is important. Arrangement is important, because ultimately in this situation also, we are dividing the data in some parts, right? So it is important that we arrange the data first, and the data is not in a haphazard manner. So 52, 54, 57, 62, 67. We again repeat the number. That can happen. That is not an issue. So these are the 15 observations. Now, if you could remember what we had studied, if we want the yth value on yth percentile, then it would be n plus 1 into y by 100. Right? So what we're trying to say is, suppose if we take an example, this y, instead of this yth percentile, suppose I want to achieve 60th percentile. Now, after computing the figure, I'll also tell you what does 60th percentile means. So if I apply the formula, it would be n. N is the number of data points. Now, the number of data points is 15 over here, so it will be 15 plus 1. Now, this n plus 1 into y by 100 is common for both odd and even. So that logic that we were applying at the time of median, the logic is no more applicable over here in case of quantiles, right? So it is 15 plus 1 into 60 by 100. So it will be 16 into 0.6, which is 9.6. Now, what does it mean? So if we take 9.6th observation, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So it will be 67 plus, it will be 74 minus 67 into 0.6. So if you compute it, it would be 4.2, 71.2. This is the value on 60th percentile. Now, what does this mean? See, we have already seen how to use this formula, right? We have already seen the usage. Now, what does it mean? So, if I vertically draw it for you, the numbers that we had discussed, if I vertically draw 89, 87, 5, 6, right? If this is the block of my data, so 60th percentile means such a value. 60th percentile means such a value which is more than which is more than or equal to 60% of the data set. Now the value we computed was 71.2, right? This was our 60th percentile. Now if you see, 71.2 is more than this many observations. So 71.2 is more than 9 observation in the data set, which means that it is more than 9 by 15% observation. 9 by 15 observation in data set. Now if you compute the ratio of 9 by 16, it would be 60% of observation, which means that 71.2 is more than 60% of the observation. That what percentile means. And this was the example which I was discussing when I was discussing about the CFA. So suppose here CFA decides that my threshold is 60 percentile, which means that all the students who are above this portion, who means all the students who are above 71.2 will only clear. This is what is meant by percentile. And this is how you compute the corresponding value of a percentile from a given data set. So the formula, if I have to repeat it once again, it is n by 1 into y by 100, where n is the data point, number of data point, and y is the required percentile. Right. So with this, we complete the concept of quantiles in full details. Next, we will start with measures of dispersion. So we will be starting with the measures of dispersion. So before we understand what are the measures, what are the different types of interpretation of those measures, it is important for us to understand what does dispersion mean. So if you look at the one liner of dispersion, it states that it is the variability around central tendency, right? Now we are thrown with two words over here. First is the variability and second is the around central tendency, right? So I would like to give a sense to you with respect to what does dispersion means and why it is important, why even this discussion of dispersion is important, right? So let us take an example around what does dispersion means and actually understanding and feeling the meaning of dispersion, right? So suppose I consider a situation where I take a revenue of company for the past 50 years. So 1972 to 2022. This is this line x-axis indicates years, right? So 50 years, and let y-axis indicate the revenue. And suppose we assume that for this type of company, the revenue is quite cyclical and dependent upon various other non-controllable factors. So this actually shows a revenue which is actually not in a particular trend, right? So this is a specific assumption that we are making for this question in order to be able to understand the concept of dispersion. So we assume that suppose in 1972 it was over here, then it rose, then it fell, then it again increased, a bit of bad phase, then like this, and then it is like, so we will assume that this is the kind of revenue trend that we are having, right, over the past 50 years. So this is the revenue trend. Now, what we will be doing, we will be computing a mean of this revenue trend. So suppose if we compute the mean of this revenue trend, for example, suppose the mean is over here, right? So what we'll do, we'll draw a line across the years. Now this is computed basis revenue of past 50 years, right? So this is computed. Now if you see one noticeable aspect of the mean and the revenue trend line is that in some year the difference between the mean and the revenue trend line is high, right? In other year it is low. Again it has increased. In some places it is very high. In some places it is very low. For example, here it is very high. However, it is on a positive direction. On the other hand, if you see over here, it is on a negative direction. Again, it is on a positive direction. Again, a bit of negative direction, but it is close to mean. At the same time, it is over positive direction, right? So what we can see over here is that if 50 years revenue is my entire data set, right? If 50-year revenue is my entire data set and I compute mean of this data set, I will find that is varying right. So I believe that you have watched my earlier classes with respect to this chapter, and I believe that you are already through with these type of an expression, what is xi, what is x bar. So I will not be explaining it again because it will be an unnecessary waste of time. So if you don't understand this expression, I would please recommend that you please watch the earlier video, then come over here, right? So xi minus x bar will be varying across observations, right? In some places you will find, in some places, in some data, if I have to say in some years, it is high. In others, it is low. So you find, so what we see, what we saw that the actual observation, which is the revenue, the observation that is the revenue is actually varying with different degrees around the mean. So if you see the revenue that we are discussing, this revenue is varying with different degree around the mean, which means that although we have a single number mean computed for the entire data set, but the actual number in the entire observation based on which mean is computed is varying at different degrees from the mean. This variation of the actual information or the actual data point or the actual observation from the mean is actually dispersion. So whenever we talk of dispersion, it should be clear in your head that, for example, if this is the mean, right? If we consider this to be a mean, so whenever we talk of dispersion, it should clearly come to the mind that your actual data is somewhere moving up and down from the mean, such that it is not equal to the mean, and the difference between the both is varying at different degrees. This difference, this variability, now I am using the term used in the definition, this variability from the central tendency. Now we have already seen that mean is a central tendency, right? So mean is a central tendency measure. So what we discussed, that variability of the actual data within an observation from the central tendency is known as dispersion. So dispersion, if I have to present it in a diagrammatic manner, this is simply dispersion, where what I am seeing is that I have a mean computed, but it is different. It is varying from different observation at different degrees. This variability is known as dispersion. Right. So whenever I'm talking about the dispersion's definition, this graph, this picture should come to your mind that I have a mean, I have a straight line, and I have certain data above it, I have certain data below it, I have some data which is far away from the mean, I have some data which is closer to the mean. So this variability of the actual information from the mean is known as dispersion. Right. So now we are clear with the definition of dispersion. However, when we talk of dispersion, there are certain measures which we are used. Similar to when we are talking about central tendency, we had three measures, right? When we were talking about central tendency, that is identifying the midpoints in a data, we had something known as mode, we had something known as median, we had something called as mean, right? We had different measures. Similarly, when we talk about dispersion, that is when we are talking about the kind of variability from the mean, we have different ways in which we depict a variability in a data. Variability as in how dispersed the data is, right? Means how varying the actual observation is from the mean. For that, we have separate measures to compute, right? So separate measures to show. The first measure is the range. Now, range is a very simple measure, and it is clearly, even the name is clearly indicating what are we trying to compute. So range is computed by maximum value minus the minimum value, right? So in many of the earlier example where we took the score achieved by students in a class, for example, 9 student in class, 10 student in class. So suppose if I take an example of, again over here, so if I consider this to be my data set, 5, 9, 10, 50, 61, 78, right? So if I consider this to be my data set, and if I'm asked to compute the range, of this data set, then I will have to simply subtract the minimum value from the maximum value, right? So the maximum value in this data set is this. The maximum value is 78 and the minimum value is 1, right? So the range would be 78 minus 1, range would be 77. Now we have learned how to compute range, right? Now the next question that you should have in your mind, and I would want that you have, right? Although it is not clearly answered in your textbook, but out of curiosity, out of more understanding, these are the questions that you should have in the mind as to what does range indicate, right? This 74, 77 I have got as a range. It indicates maximum value minus minimum value, right? But what kind of an analysis should I make from this range? What does this 77 indicate to me, right? So this range actually indicates that higher is the range, it indicates more or higher variability in the data, right? More or higher variability in data. And why I am saying that, so if you look at my example over here, which I have discussed, so if you see in this example that I have highlighted, you see at one point we have a score like 1. On the other hand, we have a score like 77, right? So you see how much, to what extent we have a diversity. At one point, we have a very low score of 1. And at the same time, we have a very high score of 78, right? So the variability, that is the range that we are having, the range that we are able to develop between maximum and minimum is very high. On the other hand, had it been, for example, had it been a data of 10, 12, 15, 16, 11, here the range would have been 6, that is 16 minus 10. So it would have indicated that the variability of the data is less, right? The data is not much variable. The data varying across the mean can actually be sensed through the kind of range that we are having, right? If my minimum value is very low, if my maximum value is very high, then the fluctuations in the data can be estimated to be very high. Now, I have again introduced a new word as fluctuation. So if you see the graph that we had drawn earlier, if you see this graph is nothing. This graph is actually showing you fluctuations, right? So it is showing you nothing apart from fluctuation. It is showing you how the revenue first increased, then it moved, then means how it is fluctuating around the mean. It is simply showing you fluctuations, right? And now, if in this example itself, in the example of this graph that we had discussed, if we have to compute the range, then how will we compute it? So, if you see in this entire point, my maximum revenue has been at this point, right? If I assume to be the highest point. And in this entire data, my minimum revenue has been this. Now, what will I do? I will simply compute, I will simply subtract this. I will simply subtract this from this. I will simply subtract this from this. The figure that I get would be the range. Now, this itself indicates, so if I take it over here and if I take it over here, so if you see, the range is so big, this entire thing is the range. Just with the size of the range, we can actually estimate how variable the data is getting. So range is nothing. It is a difference between the maximum value and minimum value. It is an indication of the variability of the data. Higher the range, higher is the chances that the data is more variable, right? The data is more varying. There are higher uncertainties with respect to the data, right? The second measure that we will be discussing is mean absolute deviation. Now, mean absolute deviation is a measure which is actually somewhat related to the features of mean that we had discussed, right? If you remember, we had discussed that sum of the deviation of each of the number from mean will always be equal to 0, right? If you could remember, we had discussed something like if you could remember this formula that we have studied in the previous class. So what we had discussed that the sum of the deviation of all observation from the mean is always 0. So what we were doing, we were computing the deviation, that is the actual observation minus the mean, and those deviation we were simply adding, right? So we also took an example where we computed it. So if we see in the next pages, yeah, over here. So if you see the deviation, the concept of sum of deviation, when we were seeing, we saw that the summation of the deviation of each observation from the mean is always 0, right? In the mean absolute deviation, we are doing something similar to that. However, we are making an amend in order to get a meaningful figure out of it, in order to get a meaningful value out of it. So what we are doing is that rather than doing a summation of deviations, just mark my words, rather than doing a summation of simple deviations, what we are doing, we are adding absolute deviations, right? Now, another question would be, what is absolute deviation? If you could notice that I have kept two straight lines over here. Two straight lines. If you could notice, I have kept two straight lines over here. These are nothing, these are modulus, or what we call as mod. Don't confuse this with the mode that we have studied. That mode is a measure of central tendency. This is actually a mathematical expression, that is modulus, which means that it converts any sign into a positive sign. It converts any sign into a positive sign, which means that mod of 2 will be equal to 2 and mod of minus 2 will also be equal to 2. Mod of minus 1 will also be equal to 1 and mod of 1 will also be equal to 1, which means that irrespective of the sign of the number that is within the modulus, everything will be converted to its positive value. Everything will become positive. Now, if you compare this with the example that we had done in the previous day, right, we got a 0 over here. We got a 0 over here for the very fact that we had some numbers in negative. On the other hand, we had some numbers which were in positive, right? When we were reading the features of mean, when we discussed that the sum of deviation of each number from the mean is always 0, it is because of the fact that some numbers will come in negative and some numbers will come in positive. However, if you imagine a situation that irrespective of whether the number is negative or positive, we add all the numbers. So if we assume that rather than this being minus 2.33, I will consider it to be 2.33 only. At the same time, rather considering it to be minus 3.33, I will assume it to be 3.33. Right? At the same time over here, we have minus 0.33. I assume it to be 0.33 only. Then you will see that the summation will never be 0. Because what we have done, we have removed all the minus sign. We have removed all the negative sign in situation where your actual observation was less than your mean. So what we are doing effectively is that if I have to take this example only, what we are doing, this situation, in this situation the number would be negative, but what I am assuming, no, it is not negative, it is positive. So I am actually drawing a mirror image. So if this is the mean, this is the variability. So what I am doing, these are the situation. If this is the mean and these are the variability, then these are the portion where I'll get positive numbers. And these are the portion where I will get negative numbers, right? Right? So the blue will be the positive numbers and the red will be the negative number. In an ideal situation, this and this will both be summed and it will be 0, right? In an ideal situation. When we talk about mean absolute deviation, what we are saying that this positive number remains as it is. However, this negative number becomes a positive number. So if this negative number is, for example, minus 15, then rather than reading it as minus 15, we will read it as plus 15. At the same time, suppose this, if this is suppose minus 21, then we will not read it as minus 21, we will read it as 21 itself. In that situation, the ultimate sum will never come out to be 0, it will be a number, right? Now, if you look at the formula, and I believe that you will be better able to understand and visualize the formula as to what it is trying to say and convey. So, mean absolute deviation is simply in the numerator we have an absolute deviation summation, which is actually indicated by summation of modulus x1 minus x bar. Again, I'll repeat the fact that I'll not explain what is x1 and what is x1 and what is x bar, what is actually this summation is indicating, because these are all covered in earlier classes. If you don't know, if you're unaware, I would request that you please go to the earlier classes and you please see what does these terms means, right? And this summation, since we are computing a mean, basically this is a mean, right? It is a mean of absolute deviation. So in order to compute the mean, we definitely know that the sum that we are achieving has to be divided with the observation, right? So we have to divide it with the total number of observations. So this is how we compute mean absolute deviation. Now, what is the logic behind it? Why are we computing it, right? So if I have to give you an example behind the logic and how is it done. So let us take a situation where we have a mean right, and this is my actual data hovering around the mean. Right, this is my actual data hovering around the mean. What we will do, we will find the difference of this x1, this is x1, this is x bar. We will find the difference between x1 and x bar. Again, what we will do, this is for example x2, this is x bar. Again, I'll find the difference between the two. Just right. Again, this is for example x3. This is again x bar. I'll find the difference between the two. Again, over here I am getting x4. This is x bar. This is the entire mean is x bar. I'm getting a difference. Over here I have x5 and x bar over here again. Right. So every year I'll get a number as in x1 minus x bar. In the second year I'll get x2 minus x bar. In the third year I'll get x3 minus x bar. In the fourth year again I'll get x4 minus x bar. In the fifth year itself I'll get x5 minus x bar. Right, so I'll get this type of number. Now what I'm trying to do when I'm computing a mean absolute deviation is that from the difference that I received, since I've already put a modulus sign, none of them are in negative, right? Since I'm already converting every of these number, because if you see this should ideally be a negative number, right? This should ideally be a negative number. But since I have placed a modulus sign in front of it, it means that everything is converted into positive, right? So if I draw a graph taking these numbers, so it can be like so I'm taking these points as arbitrary to give you an example. So this point will be x1 minus x bar. Again, this point can be x2 minus x bar. So x1 minus x bar will actually be a value, right? It can be 2, it can be 3, it can be 4, it can be 50, it can be 60, right? So based on that value, I can definitely draw a coordinate over here. x3 minus x bar. x4 minus x bar. Again, this point will be x5 minus x bar and so on and so forth. So we have a diagram like this. What we are trying to do when we are computing the mean absolute deviation is that we are trying to draw a mean from this deviation itself. See, I know it can be confusing in the first point, but it is actually a very interesting concept as to how deep we can go when we want to perform any analysis. You will be able to appreciate and understand it better. See, we had an actual data, right? The starting point was the actual data. Based on the actual data, which is this wave figure, based on this actual data which we are talking about, we computed a mean, right? This was our mean based on the actual data. Then what I did, I identified the difference between my mean and the actual data for each and every year. So what I did, I have a mean of the actual data. I subtracted that actual data from the mean for every year. And I took the absolute value of it. When I tell absolute value, which means that the sign is removed. Whenever I tell absolute value, which means that irrespective whether it is positive or negative, everything is converted into positive. So what I am doing first, I am having an actual data over here, right? I am having an actual data. This was my actual data. I computed a mean around it. Then I identified the difference of the actual data and the mean for each and every year. These are the first three steps I did. Then what I did, based on the values that I received, I computed a graph. Assuming that now what you do, when you are drawing a graph, you assume this to be your actual data. Now this is my actual data, which means that this absolute deviation is my actual data now. So initially we started with one actual data, which for example can be revenue across the years. Now based on that actual data, we computed the mean. I identified the difference between them, took their absolute value, and now these absolute values are my actual values. Now these absolute deviations are my actual value. Now considering them to be an actual value, I plot a graph and simply I try to compute a mean of those absolute deviation, that is mean of the actuals that we are considering over here. So first we have an actuals, we compute a mean out of those actuals, then we identify the difference between the actuals and the mean, right? We take their absolute values and we assume that those absolute deviation is now the number on which I have to perform the analysis, right? In order to perform an analysis of the revenue, we had an actual revenue given, right? We had a revenue. Based on the revenue, we computed a mean. Then we identified a deviation and took absolute value for those deviation. Now we are trying to perform some procedure on that absolute deviation. So the first procedure that we are performing is to simply compute a mean of that deviation, right? So simply, if you could see a pattern, a chronology, first is the actual numbers, a mean around it, computing a deviation, then converting it into an absolute form and using that absolute deviation to perform procedure on it. The first procedure is to compute the mean. Now, why are we computing the mean? So again, mean absolute deviation, as it is already given that it is a measure of central tendency, what does it indicate, right? Suppose, and it has a very strong indication. Suppose if I was given only a 5-year data and my deviations were 5, 10, 50, 18, and 34. Suppose these were my deviation for individual observations. However, when I'm presenting any analysis, when I'm showing any interpretation, I cannot actually give the deviation for 5 different years, right? When I have to comment on the data, when I have to comment on the data, that comment means when I want to comment on the data, that comment cannot be based on 5 deviations that I'm getting for 5 different years, right? You need to understand the pain point, right? Every formula in statistics has been developed in order to address some pain point. And that pain point has to be understood well in order to understand these formulas. So let me just repeat it once again. Suppose if I have to make any comment on the data with respect to its variability and I have deviations for each of them, I cannot make any comment basis 5 different deviations that I am getting, right? I need to compute one single measure which through which I can compute, through which I can comment on the variability of the data, right? So over here, suppose for 5 years I have these different deviations. Now, how can I comment as to whether the data in or data as a whole is variable or not? The easiest method is to compute a mean around it. So we all know that mean actually mean provides a mid value, right? Mean provides a mid value of the data. So for this, the mean would be 10 plus 15 plus 18 plus 34 by 5, right? So it is 30, 48, 82, 82 by 5. So it is 16.4. So now we have converted all these 5 years deviation into a single number. Now this 16.4 can be used to comment on the behavior of data. Right. Now this can be used to comment on data's behavior. This 16.4. Right. So it is very important that although you are learning a formula, but you understand as to why do we need this formula, right? There must be a need, right? Although we are studying something, there must be a need because of which this measure came up and because of which it was included in your studies, right? So you should understand why are we using these formulas? Where will we apply these formulas? Now getting back to the topic. So mean absolute deviation is simply, in the numerator we have to keep absolute deviation summation, and in the denominator it will be total observation, right? So till now we have covered two measures of dispersion. The first one is the range, the second one is the mean absolute deviation. The third one and the one of the most important one is the variance and standard deviation. It will actually not only used over here, it will be used in various places in various topics, right? So it is important that you understand this topic well. Now, within variance and standard deviation itself, we have two topics. One is the population variance and standard deviation. The second is the sample variance and standard deviation. So we will get into the formula and we'll get into the aspect. But I would request you to look through my videos because I've already discussed as to what is population, what is sample. So I again would not like to invest my time on understanding and making you understand that what do I mean by population, what do I mean by sample, because I believe by now this concept must have been clear to you. Otherwise, it is very difficult to proceed with this chapter, right? Now, if you look at the formula is almost equal for both. Variance is sigma square and standard deviation is sigma. For sample variance, it is S square and S, right? So you should be very particular with respect to the denotation that we are using, because these denominations are quite used generally, and suppose in the exam a sum comes, right? So rather than writing variance or standard deviation, they can directly give you these denotations. So in that situation, you should be able to understand what do you mean by this, What do you mean by this? How do you differentiate this from this? So it is very important that you understand these denotations. These are quite standardly used across all textbook, and it will be same across all textbook. So that won't be a problem to you, right? So population variance is given by x1 minus mu whole square by n. And simply when we are square rooting it, we'll get a standard deviation. So standard deviation is nothing. SD is nothing. It is a square root of variance, right? Both for sample or population. SD is nothing. It is a square root of variance. So the main thing is now to understand what is variance, and then we are done. Standard deviation simply is nothing. It is a square root of variance, right? So we have already learned about the denotation. This is each data in the set, right? This is the population mean. So in the previous class where we had discussed about arithmetic means, I had already specifically mentioned of this mu denotation with respect to the population mean. So if you don't know, again I'm saying that you please watch the previous video, because those concepts will now be used over here. And if you have directly moved to this video, then it will become very difficult for you to understand, right? Then even that investment of time that you are making for watching this video without knowing these denotations, without understanding these meaning, would actually not be very fruitful to you, right? So mu means population mean, and n is the total number of observation. So standard variance is nothing. It is summation of xi minus mu whole square by n, right? And when we square root it, it becomes standard deviation. Now, one important question is that why are we squaring it, right? So this should ideally come to your mind, right? When you're seeing a formula, you should be able to visualize to why we are squaring it, why we are taking the absolute values. What is my objective behind it, right? So the objective over here is very similar to what we have discussed with respect to mean absolute deviation. So we had already discussed, right, that in mean absolute deviation, what we were doing, we were taking the absolute values, right? We were taking the modulus values, because had we not taken the modulus values, the positive and the negative signs would have negated each other, and the ultimate figure would have been 0, which is one of the feature of mean, right? For the same very reason, we are squaring it. Again, when we are squaring any number, it becomes positive. So minus 2 square is also 4, and 2 square is also 4, right? So what are we doing? Ultimately, through squaring. So when I am telling this square, so what I am doing, I am actually converting the sign, any sign, it can be minus, it can be plus. I am converting this sign into a positive figure so that I can actually perform some analysis on it. Right? So I'm converting the negative or the positive sign into a positive sign when I'm doing it. Similarly, when you look at sample variance, the numerator is same. It is simply the observation minus the sample mean. However, the main difference is with respect to the denominator. The denominator is small n minus 1. Now, if you compare it with the population standard deviation, population variance, it was only capital N, which was total number of observations, right? So corresponding to capital N in the population variance, we have a small n in the sample variance. This is total number of observation in sample. Total number of observation in sample. However, we are doing a minus 1 over here. So this one peculiar thing that you have to keep in mind is that when we are computing a sample variance, my denominator will not be a small n. My denominator will be small n minus 1. which means that my denominator will be total observation minus 1. This important thing you have to keep in mind. Now, why you will have to do it is something that we will be discussing now. So for this, I have mentioned something known as concept of sample. And this is quite self-explanatory. So what does it state? A sample is usually a smaller set of the data drawn from the population, right? So this we had also earlier discussed when we were discussing about population mean and sample mean, is that if this is my entire data set, if this is my data set, if this is my data set, then or the universe, or I can call it as a population, and I draw bits and pieces from them. I draw bits and pieces from them So what I did, I have a larger population. This was my larger population. What I did, I drew bits and pieces from them to form a smaller set. This smaller set is actually known as sample. So after seeing this figure, you can actually relate and understand what I am trying to mean over here. So it means that a sample is usually a smaller set. So it is a smaller set. A sample is a smaller set over here of a data drawn from the population. This smaller set was actually drawn from this population, right? And thus there are chances. Now comes the fact as to why n minus 1. Right. My pain point was as to why I was doing a n minus 1 in denominator to compute a sample variance, right? However, we had done a simply capital N division when we were computing a population variance. So why this difference? So this why is answered in this paragraph, right? It states that since a sample is drawn as a smaller set from the population, there are chances that sample SD. What is sample SD? Sample SD, sample standard deviation. What is sample standard deviation? It is root over summation xi minus x bar square divided by n minus 1, right? So if you see over here, what is sample SD? It is summation xi minus x bar square by n whole root, right? Since it is drawn from, it is a smaller set, it is chances that sample SD will systematically underestimate population SD. Now, what does this mean? So, this means that this data was a larger data, right? With higher number of data points, we had drawn a smaller set around it, right? So, if I have to show what they are trying to say through an example, if this is my entire population and this is my mean around them, so you see the variability over here, as I can see, is higher, right? On the other hand, if I draw sample from it and try to figure out the variability, so if I draw a sample and try to so you will see that as compared to this figure, this will show a lesser variability. There are chances. I am not saying that it will show, but there are chances. So there is a probability, means it can occur. It is not in our control, right? It can occur. So what they're trying to say is that since we are drawing a smaller set, there are chances. So even this concept recognizes the fact of chance. So there is a chance that sample SD will systematically underestimate population SD. So this means that if population SD is 10, then sample SD might be 6. Right? So it states that there are chances that sample SD will systematically underestimate population SD. Hence, because of this fact that sample SD can underestimate population SD, sample variance or SD is a biased estimator of population variance. And this question comes as a direct question in your paper, right? So they'll give you 3-4 measures. They'll give you as in sample mean, population mean. They'll give you sample SD, population SD. They'll give you, for example, comparing between sample and population of some other measure, and they'll ask which of the following is a biased estimator. In that situation, you should be ready with your thinking that yes, I have read that when we were computing SD and variance, we were told that sample SD or variance is a biased estimator. So this comes a direct question. So now what to do? So now we know the problem that sample SD or variance is a biased estimator. Now what to do? So in order to improve the statistical property of S square x, now what is S square x? This is nothing. This is the variance, sample variance. So what it is saying, in order to improve the statistical property. Now what is statistical property? Statistical property means in order to make the sample variance more representative of the population variance, right? So which means that, so in the earlier example, what we told, this was our population SD or variance, and this was our sample SD or variance, right? So what it is trying to say that rather this being 6, if we try to get close to 10, which means that it can be 8.5 or it can be 9, means closer to the population figure, in order to improve the statistical property, which means that to get closer to population, to get closer to population figure, as an estimator, which means that in order to improve the statistical property of Sx as an estimator, which means that in order to come closer to the population figure, we have a denominator as n minus 1 rather than n. Now why n minus 1? So it is a very simple logic, is that in ideal situation, in most of the situation, or in situation where we have a risk, what the risk is primarily is that sample SD will be less than population SD, right? Our risk is sample SD is less than population SD, right? So how do we negate that risk? Means how do we deal with it? The only thing through which we will be able to deal with it is to increase the sample SD. Right? Now sample SD, if we consider sample SD, the formula of sample SD, if we consider it to be the same as that of population SD, so it will be xi minus x bar whole square by n, right? If we assume. However, we want to increase this figure, so we have two options. Either I add something over here. If I add something in the numerator, then the overall figure will go up. Or the second option I have is to subtract something from the denominator. Now, it would be very difficult for me to add something in the numerator that will make sense. And by now seeing so much of formulas in this chapter, you must have also understand the relevance of xi minus x bar. That is the relevance of this deviation, right? So playing with this deviation actually doesn't make sense. So in order to address this situation logically, what should a logical person do? The logical person would say that, okay, I'll reduce the denominator. Right? And this reduction of denominator has actually resulted in taking n minus 1 rather than n. So I guess with this we are actually through with the concept as to why we are using n minus 1 in sample variance and sample SD as compared to no, say only n when we are talking about population variance and SD. With this, we have actually covered our third measure of central tendency, a third measure of dispersion,